this is flow over an immersed body, right? An aerodynamics type of problem. That means Reynolds number is the one you want, not Froude, Weber, Mach, or any of the others. The drag force is going to be 1/2 times the drag coefficient times density of the fluid, the velocity squared times the area. And I'm going to go ahead and rewrite area as a dimension squared. Now that area could be something different depending on the application. It might be a cross-sectional area, or it could be the planform area of a wing, like for a lift problem. But in this case, we'll just put a generic length there, because once we do the ratios of lengths, what length or area this actually represents will end up not actually mattering. So modeling and prototype similarity problems involving drag might seem a lot more complicated than they really are, because in most textbooks, you haven't even gotten to the chapter on drag and lift yet. But the drag equation is not that complicated, and so solving these problems is still just like all of the other Reynolds number, Froude number, Weber number, modeling, similarity, similitude problems. Your goal is still to establish dynamic similarity by setting the Reynolds number or Froude number, whichever appropriate non-dimensional parameter you want, equal between the model and the prototype. And then additionally, you're going to set the drag coefficient equal between the model and the prototype. And between these two equations of model and prototype equal to each other, you should be able to solve for all of the unknowns that you're looking for. Given information about density, so I'm going to use the version of Reynolds number that has density in it, instead of the other one that's a little bit easier that has just dynamic viscosity. So I'll set up my relationships that the Reynolds number for the model and Reynolds number for the prototype have to equal drag coefficient for the model, drag coefficient for the prototype. And remember, we're setting equal the non-dimensional parameters. We're not saying that the drag forces are equal, just that the drag coefficient is equal. And since it's going to be since we're going to use the same football, we're not building a tiny little model football. We're using the same football as the model, as the prototype. All the distances are going to cancel. LM and LP are the same, and the 2D values are the same. And if you're stuck and not sure where to go next, just work backwards. Figure out what is your final answer. In this case, it's a ratio of forces. And let's actually find where that is in the equations and try to isolate it by itself so that we can figure out what we need to find to get the final answer. So since densities are given, the main thing we need to find is a ratio of the velocities. So now jumping over to the Reynolds number side, we can rearrange those terms to get a ratio of the two velocities. So we're given viscosities, given densities, so just some plug and chug, we get a ratio of the velocities of about 11.5, and that's unitless, right? Because both the numerator and denominator are the same units. So we take that whole fraction, move it over to the other side, square it, plug in more densities, and we get a final force ratio of 0.16, which means that the measured force on the experiment in the water tunnel will be larger, and that it'll actually be about 6 times smaller force on the actual prototype when it flies through air. A little interesting, we never actually solved for the velocity of the water. So if you've watched the video up here I did about Reynolds number, you can see almost every problem was about solving for the velocity of the model. That's usually the thing that you need to find, because you need to figure out what settings to put in there to run your experiment. If we did need that for this problem, we could solve that using just the Reynolds number side, not the drag coefficient at all. And we get about 2.4 meters per second in water, which is much slower than the airspeed and a very reasonable number. You could definitely build a water tunnel that could go 2.4 meters per second in order to actually set up this experiment. Indy's treadmill is a little bit loud. It might not be picking up on the microphone right now, but it's almost hard to think in here, even though he's not moving very quickly. So if you want to take a quick break, go ahead and hit the thumbs up button while you watch Indy tire himself out back there on his treadmill. We'll get back to the problem in just a second. If you're at all like me, you find these similitude problems are kind of a relief after conduit flow. Some of those problems could be really long. These ones are nice and quick. You get through them. It's kind of nice. It's a nice little change of pace. All right. Airplane problem, giant paragraph, block of text. I'm going to draw a picture in order to try to keep all these numbers straight. Probably the most common mistake for this type of problem is to use the wrong number in the wrong place, like to mix up which one's the prototype and which one is the model. So drawing yourself a picture and putting your numbers next to the appropriate picture will help you keep track of which is the prototype, which is the model. So usually vehicle problems, I would normally default to setting Reynolds number similarity. Vehicles are flow over immersed bodies or external flow problems, right? Aerodynamics, and that lends itself towards Reynolds number, which provides information about boundary layers and laminar versus turbulent flow, which is really relevant. But when we start talking really high speeds, actually the Mach number might be more relevant. A lot of times we model air as incompressible at low speeds, but it is compressible flow at higher speeds. And compressible flow is when we want to find Mach number similarity. Or like in this problem, if you're told right in the problem statement to use Mach number similarity, that's a big clue also. So if the prototype operates at Mach 0.85 and we've got the speed of sound of 340 where the model is going to be built, we can get that the velocity of the wind tunnel for the model needs to be 289 meters per second. And we're like halfway through the problem now. This is model studies is great. I really love these problems. And again, it's okay if you haven't seen drag or solved drag or lift problems yet. You can just look up the drag force equation in your textbook or just copy it down from my screen here. And what you're setting equal to each other, remember, is the drag coefficient. You're not saying the drag force is equal. The drag coefficient for the model and the prototype need to be the same. I'll rearrange these terms so I can find the thing I'm trying to find, which is a ratio of the two forces on one side of the equation and all the other junk on the other side of the equation. And to help keep yourself organized, set up all of this junk right above the coordinate terms: density above density, distance above distance, velocity above velocity. This makes it real easy to identify what you can cross off, for example, the 1/2. For velocities, we were given kilometers per hour for the airplane, so need to convert that to meters per second. That lets us plug in the velocities, and then we were also given the distances: 52 meters for the prototype, 1 meter for the model. Just waiting on Indy. Still need density. And there's one number up on my drawing that I haven't used yet: 10,000 meters of altitude. And that's going to be another clue. If there's a number you need and a number you were given that you haven't used yet, maybe it's going to be useful. So check the back of your textbook. And if you don't have it in your textbook, check online or a different textbook. There are tables where you can find density of the atmosphere, right? Density of air at different altitudes. So I can look that number up. It's about 0.4 kilograms per meters cubed. And that's a lot smaller than the density of the model because as you get higher in altitude, the air gets thinner. It gets less dense as you go higher in altitude. Plug in all the numbers and get a ratio of 940. So if you measured a 1 Newton force on your model, that would actually correspond to a 940 Newton force on the actual prototype airplane when flying at altitude. And that probably makes sense. Your model is a little teeny tiny model of the whole thing, right? Everything's much smaller on the model, not just the dimensions, but also the forces. And the actual forces required to be like drag and lift on a full-size jumbo aircraft, of course they're going to be hugely bigger. Model versus prototype similitude problems, similarity problems, almost guaranteed to be on the FE exam because they can be done so quickly, but the problems on the FE exam are probably going to be easier than these drag problems were. So if you want to see problems using Reynolds number or Froude number, which are much more applicable to the FE exam, that's these videos on the screen now.